Well, thank you for joining us for another talk in the Chemistry 2021 Senior Experience Seminar Series. Today we've got Natalie Horgan who's going to share her research with us. Stay tuned for 3 more talks next week. We also have a Tuesday 11 a.m., a Wednesday 4 o'clock, and a Thursday 4 o'clock if you're looking for your science fix. And here to give a personal warm welcome to Natalie is her advisor, Allison.
Thank you, Rachel. So I am super excited to introduce Natalie. This is when I get to embarrass her a little bit, be like, when she was a young chemist in 116 with me. No, there's something unique about Natalie that I want to absolutely share. Most students, when they learn something new or make a connection, they kind of like, oh, that's cool. Like they'll keep it within. Natalie is the exact opposite. She will tell you when she makes a connect, and it is so inspiring because she'll be like, oh, you mean this? And then what's great is she'll bring in like some other completely like different topic and then be like, oh, and that's related. And you just get to see her sciencing right in front of you. And it has been so inspiring. I've gotten to see this in my thermodynamics class, my quantum mechanics class, and in our advanced chemistry laboratory where she came up with this whole project she's about to propose to you. It was all her. Like, this just shows what great questions can yield. This is a fantastic project, and I'm so excited for her to share it with you. It's astrochemistry at a liberal arts college with no telescopes, and yet she's been able to bring together pretty much all of her work that she's done. Oh, not to mention that she's also done work with Deanna Donahue, and I totally forgot to mention this, was it the TDA stuff with Artemis? You have like dabbled in almost every aspect of chemistry, and now you're taking it to the stars. So it has been an absolute pleasure to have you in class. You're an inspiring student, and I wish you the best from here. And I'm super excited that you're going to share some really cool data with everybody else. So Natalie, take it away.
So good afternoon. Like Allison said, my name is Natalie Horgan, and today I'll be talking to you about the field of astrochemistry as a whole and how molecules in space are identified. And in particular, I'll be discussing my specific research into the characterization of glycine precursors, and as well as their reactions as a way to approach how research in this field is performed. Now, you might think that looking at like glycine or these crazy molecules in space is just some far-fetched idea, but complex organic molecules like the buckyball have already been found in space. The formula for this buckyball is C60, which means that it actually is 60 different carbon atoms formed together, linked together through some bonds. And that's a lot of carbon in one space to be found in space. There are also other molecules in space that have the same atoms that you could find in glycine, which is shown on the right of the screen. So there's blue, which is your nitrogen, red, which is your oxygen, H is hydrogen, and then the black color is your carbon. And if glycine is found, we need to be able to figure out how it was formed, and that's where the reactions that I was looking at come into play. So before we even get into that, we have to figure out where in space these molecules would be found. And to look at that, we have to see the interstellar medium, the ISM, which is the space between stars in the universe. It's predominantly made up of dust and gas, and there is a ton of different environments with different wide-ranging temperatures. These environments mainly fall into 3 main temperatures: your cold, your warm, and your hot interstellar medium. And usually you'd think that's just a small variation when you're thinking of Earth temperatures, but when it comes to space, that's a really, really wide range. What you see in front of you are 2 different forms of the interstellar medium. On the left, you see a dark nebula, the Lens Dark Nebula, and on the right is the Cygnus Loop. The Cygnus Loop is the hot interstellar medium. It's an example of that. It This is formed through supernova explosions. So when you have a supernova explosion, you have a lot of heat that will heat up gas in the interstellar medium, and that's how you can get this kind of environment. This is actually heated up to like 10 million Kelvin, which ionizes the gas to make plasma out of it. Another place that you would see plasma is lightning. And then on the left is the dark nebula, which is more of interest for what I'm looking at for molecule formation. And this is the complete opposite. This is 10 Kelvin, which is just above absolute zero. That would be equivalent to about 50 degrees Fahrenheit above absolute zero. So this is very, very, very cold. This is where you can find molecules in space. So we know this is where you can find molecules, but how do we see them? And that's where spectroscopy comes into play. On the very left, this is what you would see, kind of like if you had a prism or something. You have a light source, and then when you're looking at just the visual spectrum, you see just a rainbow of colors. Now, when you have something like a gas cloud and you have a light behind it that shines through this material, the molecules, the gas, whatever's in it can absorb light at a certain wavelength or frequency. And then when you look at the light that comes out of it, you'll be missing a specific wavelength or wavelengths of light. So if you see this spectra in the middle, you'll see the whole range of the rainbow colors, but you're missing just a little bit in the orange. You're missing that particular color. And that would be absorption, which is what I'm looking at in particular for this research. Another form of spectroscopy is emission, which is on the far right, where you don't have a light source and you have the gas or the molecule emitting at a specific wavelength of light. It corresponds with what is absorbed in the middle. Okay, so how do you even figure out where to look, what's getting absorbed? How do you do this kind of research? Yeah, you can observe the light and what's going on in space through telescopes and stuff like that, but how do you actually do research? And that is where you have different forms of science. So you have your experimental modeling, your calculations, and your observations. And these all work together for you to gain knowledge of what goes on in space. On the left, that is Planck, which is one of the it's one of the satellites and stuff that was orbiting in space. It's no longer active, but it looks at a certain part of the spectra called the microwave region. That's where you would look at the spectra like we saw at the previous slide. In the bottom right, that's a supercomputer. So this is where you would do the majority of your calculations to do more P-Chemie, physical chemistry, theoretical type research. You're going to want to have, you're not going to want to do all that by hand. And that's where these big computers come into play, so you can do those calculations. In the upper right, that is a picture of a experimental modeling laboratory. And this is how you can kind of do laboratory research for stuff that happens in space. You make these huge instruments that can simulate cold temperatures and the type of pressure you need to try and figure out how reactions would occur when they're in space without actually being there. So you have all these 4 different ways of looking at space, either by modeling on Earth or your calculations or the actual observations that you can get from telescopes and satellites. And when those work together, you can have this really interesting triangle and collaboration between a whole bunch of different kinds of scientists to learn about the interstellar medium and different areas in space without actually physically sampling what's going on. Lots of the interstellar medium and all these different places that you want to look are light years away. It's just not feasible or possible for us to actually go out there and research and try and take like a picture or whatever when we're like go and take a picture or take a sample out in the interstellar medium. It doesn't make a ton of sense. There's also really, really low densities. So even if you got there, it'd be really hard to get a physical sample because these molecules are so far apart. So to do that and to overcome that barrier, you have these 3 different areas of research working together. My research in particular falls into this calculations area. We don't have an astrochemistry lab here. It's a liberal arts education, right? So you can't really do experimental modeling because that's very those aren't instruments you can just go and buy, and they're ones that you have to make yourself. And there's usually really big laboratories at huge research universities that do that. And then but the calculations aspect, even though it might seem more boring or simple than the other more interesting ways to look at space, it's integral to figuring out what's actually going on. So why is it important to understand what's out there in space? It helps us answer those big questions, or at least try to figure out if there's life out there. Not necessarily the little green man, but is there some microbial matter, or is there life out there, or how did life begin? Where do the molecules that we have on Earth, where did they start? Did they start on Earth, or did they start somewhere up in space? And that makes it really, really interesting for scientists to try and grapple with these really huge questions and try and solve them in very small ways. So if, for example, the buckyball or other molecules like carboxyl anion that have been found in space, these are complex organic molecules that you can find in nature on Earth. So they're also being found in space. Did they start here? Did they start in space? Did they start on a different planet? We don't know. And it helps to try and figure those out. They're really interesting questions to try and answer. And in particular, one molecule that's of interest and is searched for in the ISM is glycine, which you can see on the screen in front of you. Glycine is a complex organic molecule, and it's really significant because it's connected to life. It's thought to be in possibly interstellar ices that you can find in the interstellar medium. And the 4 reactions that I'm going to show you in a minute that I'm looking for all result in the formation of glycine. And because it's such a big question, where is glycine? Is it out there? Knowing how it's formed or how it could be formed in the interstellar medium is really interesting, because if we do find glycine, the next question that's going to be asked is how does it form? How is it made in the interstellar medium? And that's where these reactions will come into play. Glycine is really important in life because it's an amino acid, which is one of the building blocks of life itself. 20% of you is made up of proteins, which are made up of amino acids. Glycine is also the simplest of the amino acids. It has just an H instead of a longer R group attached to it. So if you can find glycine or how it's made in the interstellar medium, it can lead to even further questions about where life began. On the screen in front of you are the 4 reactions that I'm looking for. So you have glycine, which you've already seen. That's the product of the reactions. Dr. Garrett, in one of the articles that I was reading, was focused on glycine, and these are 4 of the reactions that have been proposed across multiple articles for the possible formation of glycine in the interstellar medium. So these 4 reactions in particular are the ones that I was really, really interested in. And I was trying to characterize the precursors and figure out which reaction would be favored and which one would be most likely to be seen in the interstellar medium. Back to the same picture again. This is the chemical fingerprint, right? So you need to be able to tell which molecule you're looking at, and that's where the spectra and how you're able to see in the interstellar medium comes into play. So we were looking at, okay, there's a gas cloud with molecules, and that's why you're missing a specific color in your spectra. And this is really important in figuring out what molecules are in space, because different molecules will absorb light at different wavelengths. So you have your visual spectra, which is your prism rainbow, and then you have different parts of the electromagnetic spectrum, and different molecules will have different absorption lines that are unique to them. And if you can figure out what the spectra will look like, if you can simulate that, then you can figure out what people that are making the observations should look for. And that in particular is where my research comes into play. You may be thinking, how does this even happen? Why is this unique? And how can you simulate spectra? And the answer to that is the kinds of motion that molecules do. The molecule on the screen is carbon dioxide. On the far left, you have your vibrational motion. Your vibrational motion is where you have your symmetric stretching. So the molecule will stretch in the same way at the same time. So you're not going to have one coming in, one of the bonds compressing in and the other one going out. That would be your asymmetric stretching. So you'd have your bending and stuff like that, where where it kind of goes up and down, your symmetric, and then your asymmetric. There's other forms of vibrational motion as well, but these are 3 of the more common ones that you'll see. In the middle, there's your rotational motion. So that's if you imagine a molecule on a XYZ axis. We have a linear molecule here, which is a little easier to visualize. So the central molecule goes into the very middle of the vertice, the very middle of the plot, and then it will spin around the X, the Y, or the Z axis, and that will correspond to a different constant for each molecule. Each rotation will correspond to a different constant. Here you only see the molecule spinning along the Y and the Z axis. That's because it's linear and it's along the X axis. So if you imagine that spinning, the molecules are going to stay in the same place. There's not really going to be any difference in symmetry because of it. And when you get to more complex molecules, then there will be differences with each of the rotations. On the far right, that's translational motion. That's just the molecule moving through space. And each of these motions will show up on spectra because they'll move with an increase in energy that comes from the light source. And that's where your little dark bands come from. So for my research, I'm simulating these spectra so that you'd be able to find one of these precursors, or you'd be able to recognize it, would be a better term to use, to be able to recognize the molecules if they're found in space, because you can base what the spectra look like to what the theoretical ones that I simulated are. To go through this process, I'll be focusing on my carboxyl group here. Instead of showing you all 8 of them, just for ease of understanding. So the lines, as I mentioned, can be simulated by finding your rotational and vibrational constants. The 3 numbers you see on this screen are the rotational constant for this molecule. So if you can imagine the little molecule I have next to the COOH, if you can imagine that molecule kind of where the carbon dioxide molecule is, it would be spinning around the X, the Y, and the Z axis, which is where you get those 3 different numbers. Each of the axes, the center of rotations, will correspond to a different rotational constant. These rotational constants, if you multiply them by 2, you'll get your simulated spectral line. So, for example, the first one, the rotational constant is 4.698 inverse centimeters. And when you multiply that by 2, you get about 9.4. And that is where the simulated spectral line for that one rotational constant is. This is what a infrared spectra for the molecule is. This would be your vibrational mode, so that bending or that stretching. Each of these are for a different vibration. And as you can see, this is also wave number, and they're much, much higher than what the rotation was. So if I zoom in to the beginning and put the rotational spectral lines that I calculated earlier, so the 9.396, so that was about 9.4. And then if I also multiplied those other 2 rotational constants by 2, I get these 3 different simulated spectral lines. And that would be really close to that 0 because they're very, very much smaller than the infrared vibrational spectral lines, which are all above 500. Now, these spectra, they're impacted by the expansion of the universe, the rotation of different objects in space, different clouds of dust that kind of can obscure your view. All these different things can impact whether or not the spectra looks like the one that is simulated. For example, these molecules will be really, really far away. If they're moving away from you, then the spectra will shift towards the red end of the electromagnetic spectrum. You see that the distance between each of the black lines is the same, but they're all going to be shifted over. And this is kind of like the Doppler effect that you hear in everyday life. So when a car speeds towards you and then away from you, where you hear the frequency pick up and then decrease, it's the same kind of idea. as the redshift. And then if the object is moving towards you, it will have a blue shift, so shift more towards the blue or purple end of the spectra. And this is as if the molecule will be moving towards you, so kind of like that bus driving towards you when you hear that. Same idea. So now that I've talked about how I characterized the molecules so that you'd be able to identify them if they're found in the interstellar medium, I also looked at the reactions themselves. So I calculated the Gibbs free energy of reaction, and this told me that all 4 of these reactions are spontaneous. Reaction 4 had the lowest Gibbs free energy, but they're all fairly close in value and they're all spontaneous. So this doesn't really give you the best idea of which of these reactions would be favored, but it's still significant because it means that each of these reactions could occur in the interstellar medium spontaneously. That means that if the reactants came into contact with each other in the interstellar medium, they would become glycine. However, the next step then would have to be which one of these molecules and which one of these reactions is actually the most favored. And for that, you'd have to determine the activation energy. The activation energy is where you have your reactants, so the precursors I was looking at, and then you have your final state, your product, so that's the glycine. The activation energy is how much energy it takes for the reactants to become the products. This is your kind of like potential energy on your y-axis, so that's, and then you have your coordinates, your reaction coordinates on the x-axis. So when your reactants need a certain amount of energy to kind of get over this potential energy hump to get to the products. And the smaller that activation energy is, the more favored the reaction is. So although that reaction 4 had the smallest Gibbs free energy, it's not necessarily going to have the smallest activation energy. So I can't say for sure that that reaction is the most favored, which is why the next step would be to use transition state theory to figure out which of the 4 reactions has the lowest activation energy, and therefore which one is the most favored and which one will be most likely to occur in the interstellar medium. Finally, where my research and where it fits in. So we started off kind of talking about glycine and its importance. That's one of the main questions is about glycine in the research, is about glycine in the interstellar medium. And my research fits here into the calculations. So I was able to determine the rotational constants and simulate what the spectra would look like for these molecules. So the research that I did can go into some sort of data bank for the observationists to look at and be able to use to see whether or not the spectra that they have could be the molecules that I was looking at. And then here's my sources. I'm now open to questions, and thank you so much for listening to my talk.
Excellent work, Natalie. I think Natalie will be willing to take questions at this time. Vivian, why don't you go ahead?
Yeah, I was just kind of wondering why the rotational constants are so much smaller than the bending and stretching.
Okay, so so energy is quantized, right? Your energy levels are quantized, and your vibrational levels are much larger than your rotational levels are. So you have the rotational levels are smaller amount packets of energy that you're increasing. So because they have a smaller wave number, because it's going to be your change in rotational energy,
Okay,
which
so
is
like
going to be smaller than your
less
vibrational energy.
check. Thank you.
No problem.
Joe?
Hi, Natalie. Great talk.
Thank
I
you.
was just wondering, so glycine seems to be a very essential molecule to look into, but I was wondering if you know there are other kinds of amino acids or other organic molecules that would be important in astrochemistry research.
Yeah, I mean, well, it would be awesome to find all of all of the amino acids in the interstellar medium. I was mainly looking at this one because it's the most simple, which is also why other people are looking at it. Leucine, I believe, is also of interest and being looked for currently in the interstellar medium. People are just mainly focusing, I think, on glycine because they think because it's a simpler molecule and more likely to be found, I suppose.
That makes a lot of sense. Thank you.
Yeah.
Stefan, did you have a question? No? Other questions for Natalie? Kelly?
Hi, Natalie. Great job. Great talk.
Thanks, Kelly.
Question about the instruments that astrochemists use. Like, what other types of stuff do you guys use to characterize molecules?
Okay, so lots of it is through calculations. Different kind, it's pretty much all spectroscopy. So we'll have you'll have lots of it's IR. Microwave is probably the most common. Experimental, I don't know as much about. That's from what I understand, that's more that's more reactions themselves. So for example, the picture that I have for experimental modeling, they're looking at, I believe it was H3 plus and neutral carbon and the reactions that those would have with each other in space environments, basically. So if you're looking at more complex things, that tends to be more calculation and observation. And if you're looking at simpler reactions, that tends to be more experimental modeling.
I can help with this too, if you don't mind, Natalie. I was good friends with the astrochemists at UC Davis. Most of what they have to build is the synthesis part, like creating the molecules and the fragments and at the appropriate 50 degrees below, 50 degrees above absolute zero temperatures. And then I think the measurement tools are pretty familiar ones that we use every day. It's the getting the molecules into existence part that's the tricky part, and the measuring that's the easier after effect. Jojo.
Yeah, I was wondering, you said that other people are looking at glycine to see if they can find it in the interstitial space. I was wondering who is doing that specifically. Like, have you looked into like collaborating somehow with them? I know that'd be big.
It would be really cool. The main person that I saw in terms of research was Dr. Garrett at the University of Virginia. That's the main. He has a really comprehensive, like 40-page paper looking at glycine itself. And he did a lot of stuff with rates of reaction. And he had, like the first part of it was kind of lit review-y almost. So he had a whole bunch of, so the reactions that I had in my presentation were reactions that were looked at by other scientists, and he kind of compiled it all into one place. And then he did a bunch of stuff with rates and glycine itself. There's a couple other people, but I can't think of their name off the top of my head, to be honest, because he's really just the main one that I saw.
Just gonna add a comment.
Oh, yes, I can bring up my live camera.
Can I add a comment real quick?
Yeah.
One of the things I want to just point out is that Natalie did all of this work with an online open source computational program that we used in the Chem 485 Advanced Chemistry Laboratory class, which was kind of limited in its capabilities, and she was able to stretch the capabilities of it. And so I think one of the coolest things about this project is how to do it with such limited resources and to get data that make sense. And so that was just a high five from a distance, shout out. So anyway, it just goes to show the power of computational chemistry, that it can answer these really cool questions with very limited and or minimal resources. So dream big, space-wise.
I have a question for you, Natalie. What other small molecules would be good targets? So you did glycine, and I think you mentioned leucine. Amino acids, is that like what we're latching onto? Is all of space amino acids, or are there other sort of more organic oriented things?
No, amino acids are not the only thing. That's mainly what I focused on, was glycine and stuff, because I thought it was really interesting in terms of the relationship to life itself. Some other people are looking at more complex organic molecules as a whole, like the buckyball, for example. There's some people that are looking at amino compounds, or not amino acids, just like stuff with amino groups. And then there's lots of people are looking at stuff with oxygen compounds. So lots of it focuses, from what I saw, around carbon, oxygen, and kind of nitrogen, and those molecules surround with those atoms. Of course, my research, since I was mainly looking at amino acids, most of the papers I read was kind of biased in that direction. So I could definitely see people looking at like sulfur and stuff like that as well, because I think that would be really interesting. Things that are more connected to RNA as well, because there's like a lot of interest in the RNA world hypothesis, which is really quite interesting. Basically, the life on, or kind of like basically life started with RNA, and then it kind of evolved from there. So there's been research done into very small RNA type molecules as well.
That's interesting. I wonder if anyone studied silicon. Silicon is like the alternative carbon, and some astrochemists predict that there might be entire civilizations built around silicon instead of carbon, like we are on Earth. So
yeah, it would be really interesting.
I think there's actually, there was one of the probes on the Cassini spacecraft was actually designed to monitor for silicon as well. It was just one of the sensors that they had.
Nice. Other questions for Natalie?
Cool.
All questioned out. All right, let's thank Natalie again for her awesome performance.
Thank you guys for listening so well.
Excellent audience, good emojis, and join us next week for our other senior seminars if you're interested.